Unit 2, Lesson 11, Interpreting Graphs of Proportional Relationships. Let's first review these learning targets before we start our lesson. It says, I can draw the graph of a proportional relationship given a single point on the graph, other than the origin. So it will not be the origin, be some other x and y value. Number 2, I can find the constant of proportionality, that is my k value, from the graph. Remember, the k is always equal to y over x. That'll come in handy as we find that. And 3, I understand the information given by graphs of proportional relationships that are made up of points on a line, points or a line. And just as a quick review, we have an example of a graph up here. Remember, if it's a proportional relationship, it's going to be a straight line, and it has to go through our origin or our zero point. That's what visually indicates to us that we have a proportional relationships. We'll keep that in mind as we move forward. So we're going to start here. 11.2, Tyler's walk. Tyler was at the amusement park. He walked at a steady pace from the ticket booth to the bumper cars. At a steady pace from the ticket booth to the bumper cars. Number 1 says, the point on the graph shows his arrival at the bumper cars. What do the coordinates of the point tell us about the situation? So we only have one point on a graph. Remember, when we look at a point, we can think of that as a set of x and y values. So our x value is 40 and the y value is 50. So in order to define this, I have to think, what is the title of the graph? We have elapsed times on my x-axis down here. Elapsed time. So it took 40 seconds to do what? That will be interpreted by our y portion here. It's the distance from the ticket booth. So he was walking at a steady pace to the ticket booth. We know it took 40 seconds to go 50 meters. Okay, it took him 40 seconds to go 50 meters. So we're going to write that for our answer for number 1. So what does it tell us? It took Tyler 40 seconds to walk 50 meters. So that's what we can gather from just looking at that point on the grid. Number 2 says, the table representing Tyler's walk shows other values of time and distance. Complete the table and then next plot the pairs of values on the grid. So let's take a closer look at our table here. We know it's proportional. It's got the point 0, 0, 20, 25, 30, 37.5, 40, and 50. And we're missing the one that's next to the 1. So we have to get our constant of proportionality. And we can get that by dividing any of these that are in the second column. We can think of the time is on the x-axis and the distance is on the y. Remember, k is always equal to y over x. We don't use the 0, 0 because that'll just give us 0. We use any of these other ones, so it's 25 divided by 20, or 37.5 divided by 30, and 50 divided by 40. All of those will give us the same number, 25 divided by 20. That's 1 1/4 or 1.25. So all of these, if you check them, you'll get 1.25 or 1 1/4. And so where our 1 is below, we're going to put 1.25 next to it. That means he's going 1.25 meters for every second that he walks. So those are our points. We're going to go ahead and plot those on the graph above. We have 0, 0. I'm going to put a big dot right there. And then 20, 25. So 20 on the x-axis and up to 25. Have a point here. 30 and 37.5. So we go over to 30 and then up to 37.5. Notice we have 30 and 40 on our graph. So 35 is that one line there. So again, it's 30 and 37.5. 30 and 37.5 will give us right here. And our next one is 40, 50. We also could put 1 and 1.25. That's going to be very hard to put on here because we have 0 and 10, but 1 would be somewhere right here and 1.25 would be right here. So it'd be very close to our origin. That's 1 and 1.25. Now it says, what does the point 0, 0 mean in this situation? So when we think about Tyler walking at a steady pace from the ticket booth to the bumper cars, 0 means 0 time has elapsed and 0 distance has been traveled. It's the time before he starts walking to the bumper cars. So I'm going to say Tyler has yet to start going to the bumper cars. It's the time before he actually starts walking them. That's what 0, 0. It's before everything starts. Now, number 4 says, how far away from the ticket booth was Tyler after 1 second? Well, we know that's 1.25 meters because that was one of our points down here. That's our constant of proportionality, so I'm going to put 1.25 meters. And 5, what is the constant of proportionality for the relationship between time and distance? And what does it tell you about Tyler's walk? Well, we've kind of said that multiple times. It means he's walking 1.25 meters per second. It's his speed, or his rate of walking, 1.25 meters per second. And we can see that on the graph where we have the 1 and 1.25. So whenever we have our x value of 1, the y value will be the constant of proportionality on our graph. Now in this case, what we could have done is also put a solid line through our graph because he's walking consistently the whole time from one point to the other. And so having a solid line shows that we have that straight line that goes through the origin. It is a proportional relationship because he's walking in the same steady pace of 1.25 meters per second. Part 2 of Tyler's walk. Are you ready for more? If Tyler wanted to get to the bumper cars in half the time, how would the graph representing his walk change? How would the table change? And what about the constant of proportionality? So let's think about it. If he's going to go to the bumper cars in half the time, that means he's going to have to walk twice as fast. So to go half the time, we'll have to walk twice as fast, or even go for a slight jog. Let's think about what this is going to look like by first looking at our graph. So originally it took him 40 seconds to go to the 50 meters. Well, if he gets there in half the time, our x value, instead of being 40, will change to 20. But the distance to the bumper cars does not change. So I'm going to put the point 2050 on our grid. Here's 2050. It took him half the amount of time to go that same 50 meters. It would still be a proportional relationship. It would be a straight line, but our rate that he's walking will be a lot faster. I could do that by doing 50 divided by 20 to get the actual number. So 50 divided by 20, that's the same thing as 5 over 2, or 2.5. And remember, in the context of this situation, that's the meters per second that he's walking. So he would have to walk twice as fast. It was 1.25, but it would be 2.5 if I change this. So again, let's look at this graph for a second. If he is walking twice as fast, it's important to notice the steepness of that. The faster he's walking, the steeper the line. Our ending point, or that 50 meters on our y, is the same ending point, but the steepness tells us that the rate is faster. So whenever we're looking at a line, the steeper line that goes to the same height usually means it's the faster rate. That's key to keep in mind when you're looking at these proportional relationships.